This is the lecture for Wednesday, April 15th. Today we will finish our discussion of the quark-gluon plasma. We will cover the topics of thermal photons, virtual photons, and dileptons, as well as the baryon-meson anomaly, and we will then briefly talk about the electron-ion collider. So first, to talk about the radiation that we see in these heavy ion collisions. So, as we've been discussing, we have these two heavy ions colliding with each other. We have the formation of a quark-gluon plasma. And the idea is that instead of looking for the hadrons, these strongly interacting particles, we actually look for photons. Okay? So these thermal photons would be coming off of the quark-gluon plasma. And here is a plot of these photons as a function of the transverse momentum. And here is the multiplicity that we see, the number of photons that we see, versus the transverse momentum of the photon. And at very high transverse momentum, remember that at high energies, perturbation theory ends up working, that the strong interactions, quantum chromodynamics is weakly interacting at very high energies. And so we can write down the simplest possible Feynman diagrams that will then give an accurate prediction of what goes on at high energies. And it turns out that at high energies it does make a good prediction. So you can see here is the next to leading order calculation. That means not the simplest would be leading order, but the next to leading order diagrams using perturbative quantum chromodynamics. And that's this line here, and it goes through the data quite well. Now at low energies you see there's a deviation, and that's because the quantum chromodynamics is not so weakly interacting at lower energies. But we can still see that on this log plot, the semi-log plot here, where it's logarithmic in the vertical axis, we see a straight line, which is indicative of a exponential decay because it's sloping downwards. And so what we see is that that this is actually an exponential decay, which corresponds with the temperature of 304 megaelectron volts. So basically you write down a Boltzmann distribution, and that fits pretty well with what's seen here, suggesting that these photons are thermal in the sense that it's sort of like you have this hot quark-gluon plasma and there's light being emitted, just like if you were burning something and you see the embers and you see the light coming off that's being emitted. Now, we can take a look at what the corresponding plot looks like. So this is the plot that you get from the Large Hadron Collider, that's ALICE. You can see also what you get at somewhat lower energies from the Relativistic Heavy Ion Collider, RHIC. And so you can see the same sort of behavior. There's a fit to the perturbative QCD here, okay? And then you can also measure at lower transverse momentum what this exponential behavior is giving the temperature, and in this case the temperature is about 221 megaelectron volts. So this was lead at the Large Hadron Collider that gives the temperature of 304 MeV, and this is for gold-gold collisions producing thermal photons corresponding with the temperature of 221 megaelectron volts. Now, we can also look at not just thermal photons, not actual photons, but virtual photons. So remember, virtual photons are these photons that are not actually, a real photon is one that you measure in a detector, or maybe even you see with your eye, okay? A virtual photon is something where we have a photon, but it does something else. It for example, produces an electron and a positron pair. Okay, this is what we call a dilepton. And that's what we're going to be talking about here. Instead of seeing the actual photon, we actually see in the detectors the, these dileptons. Now, the reason we look for dileptons is because once the photon becomes these leptons, electron, positron, they no longer interact strongly through quantum chromodynamics, and so they're very clean probes in that they will essentially just fly out and be relatively undisturbed. Now, they do interact through, for example, electromagnetic interactions, but the electromagnetic interactions are relatively weak. So that's what we're looking at here. Now, the advantage of looking for these dileptons is that this photon now, which is part of some process, maybe we have some quarks here that produced it, okay? Because this virtual photon is not being observed, it does not have to have the energy momentum relationship that a real photon has. So for a real photon, we have to have this relationship that E squared is equal to P squared plus M squared. So I'm using units where the speed of light is equal to 1. But if we have a virtual particle, then this is not necessarily the case. And so what you end up getting is you can have this virtual particle behaving as if it's at an energy that's higher, that's higher than that for a real photon. For example, you could have this energy corresponding with an m squared value. So I can rewrite this as m squared is then e squared minus p squared. Okay, and so I can record now for this virtual photon larger values of e squared minus p squared. So for a physical photon, this would have to be essentially 0. This has to be 0. E squared has to equal p squared. But for a virtual photon, this can be much bigger than 0. And that's what we'll be talking about here. So we're measuring here the invariant mass of the dilepton pair, the square root of this guy that we were just talking about here, the square root of this quantity. And so we're looking at these virtual photons producing dileptons. And here is the results that you see for the number of dilepton pairs versus the invariant mass. This is for a proton-proton collision here. And you see nice peaks here. And there are simple explanations of what these peaks are. Okay, so there's this first peak here is at about 770 megaelectron volts, or 0.77 gigaelectron volts, and that corresponds with the peak for the rho meson. So remember we talked about these vector mesons. So the rho meson, rho, has a mass of about 770 MeV. Okay, but there's another one called the omega. So these are 1 minus jp, j pi equals 1 minus. So spin 1, negative parity. And the omega has a mass of about 783 MeV, so they're very close to each other. And that's what you see here. They're resonances. They're unstable particles. So you see this rather sharp peak here. Now, there's at a slightly higher energy, you have the peak for the phi meson, so that's about 1020 MeV, and so you can see that here as well. So the phi is basically at the simplest level looks like an S bar S, whereas the rhos involve the U D or U bar D or D bar U or U bar U, and the omega also involves the U bar U with the D bar D. Okay. Now, so we see these peaks. Now, if we look at the heavy ion collisions, so this is gold-gold collisions at the relativistic heavy ion collider, what we see is that, and this is as a function of centrality. So these 0 to 10% is basically how close they are to being, 0 meaning they're completely overlapped with each other. They're very central collisions. 10% means that they're 10% off. Okay, and this is even more peripheral, 10 to 20%, and then 20 to 40%, 40 to 60%, and 60 to 92%. So these are very peripheral collisions, sort of glancing collisions between the ions. And so what you see is for the glancing collisions, the very peripheral collisions, the behavior is very similar to what you see for the proton-proton collisions. You see these peaks. Okay? In fact, these lines are just reproducing, again, the line is the proton-proton data, but the points are the actual heavy ion data. So you can see they're in pretty good agreement, but you see there's some discrepancies now that are starting to form. As you get to more and more central collisions, you see that there are these, what you see is a gradual widening of these distributions. In fact, you see a shift of these peaks to lower masses. And remember, this is the invariant mass. This quantity I said, you take the square root of this guy, e squared minus p squared, where e is the total total energy of this pair, and p is the total momentum of this pair. You see there's a shift in broad as well as a broadening of the peak. And so this is what sometimes is called the vector meson or rho meson melting. The idea that we have this resonance, but in the medium, the properties of this rho meson, which is a rather sharp resonance with a well-defined peak, it starts to behave like a slightly less massive particle, with a larger decay width. And so this is what's called in-medium modification of the rho meson. And you can imagine why this might happen. So that you have your rho meson, which let's say you have, let's make it a rho plus meson. So then you have u d bar. Okay. So this you have your quark, your up, and then you have your anti-down. But if you're in the medium, in the quark-gluon plasma, you have all these other quarks here that would modify the interactions between these two guys. So you can very easily see how perhaps these would decay apart. This would behave like a not quite as stably as it would in vacuum as a result. It would have a tendency to fall apart. Now, the fact that it actually decreases in mass is also a very interesting question that we will it's mentioned right here, what's called the possibility of chirosymmetry restoration. So let me just briefly talk about that. So chirosymmetry, remember we talked about, was the symmetry, the approximate symmetry, the fact that the up quark mass and the down quark mass are very small. Okay? And so in the limit that the masses are zero, then we have the fact that the left-handed and the right-handed helicities are decoupling from each other. Now, but what happens in quantum chromodynamics is that we have a spontaneous symmetry breaking of this this chirosymmetry, and what happens is that the mass of the pions are very small as a result. Okay. However, the mass of the rho meson is relatively large, so that's why it's at 770 MeV, and the mass of the pions at about 139 MeV. Okay, so there's quite a bit of a difference between the two, and in fact, in the limit that the light quark masses go to zero, this one goes to zero, whereas this one just stays around 770 MeV. Now, there is this idea that perhaps in the quark-gluon plasma, we have deconfinement, then in other words, quark confinement goes away, but also this spontaneous symmetry breaking that makes these two masses very different go away. And so in that, this idea of having restoration of the chirosymmetry, the idea is that perhaps the mass of the rho is starting to get closer to zero, that it's decreasing as a result. In fact, there's a name to this, it's called vector symmetry, but that's not so important here. All right? And here's more data for these the low mass region for the dilepton. So you see the rho and the phi peak. All right? And you can see here so some predictions. What you do is you make some predictions where you take the background data as well as, so maybe you can see here a little bit better. you can make some predictions where you take the background expected results from the quark gluon plasma, but then you also have the contribution from the resonances, and what you see is there's an excess above what you expected from the background, suggesting that perhaps there would be some sort of modification of the actual properties of the rho meson, as well as the phi. Okay, so this is just showing you the excess that you see in this region here from 0.15 to 0.75, okay, above what you expected from background. You see there's quite a significant enhancement, all right? And so something non-trivial is going on, perhaps the melting of the rho meson. And here is just more data showing that this excess above background is noticeable in for all different energy scales, from 20 GeV to 60 GeV to 200 GeV. All right, the next thing we'll talk about is something that's called the baryon meson anomaly. And this occurs at relatively low transverse momentum of 7 gigaelectron volts. So remember, we've said it, but let me just remind you what is transverse momentum. So we have some beam axis where we have one ion coming like this and the other one coming in like this. They collide. So the transverse momentum is just basically how much momentum you have flowing transverse to the beam axis. Now, if you take a look at the multiplicity of proton-antiproton pairs over the pion-antipion, or pi plus plus pi minus pairs, and plot it as a function of the transverse momentum, what you see is that as you look at the, okay, so here is a plot of the various different cases. All right, so we have here the proton-proton collision is the data right here with a energy of about 7 tera-electron volts. Here's the data like this. Okay, now I'm going to show you the peripheral collisions where the overlap is not very good. Okay, is not very central. So that's shown here in the blue. Okay, this ratio is increasing relative to the proton-proton collision, but not that much. But then you get a little bit more central. That's what's shown in the green here. And you can see a bigger peak. And then if you go to the very central collisions, so where they're really lined up, okay, then we see a nice big peak here. There's a couple things you'll notice is that at large transverse momentum, they all fold onto each other. That what you see for the ratio of proton-antiproton over pi plus, pi minus, is sort of universal, that everything behaves the same here. That's kind of interesting. We'll come back to that in a moment. But at low transverse momentum, we see that there's a big difference between the central collisions as opposed to the peripheral collisions, which are closer to the proton-proton cases. Okay, so here's just this is data that's coming from Elise. Okay, and this is for as we said, proton-antiproton over pi plus pi minus. Now this is data coming from lambda, another baryon pair, lambda bar, over the K0, the kaons. And so what you see here is the same sort of behavior going on. That there's some sort of, this is what's called the baryon meson anomaly. So what could be causing that? There seems to be out here above, let's say 8 GeV or so, we have universal behavior, but below 8 GeV we have non-universal behavior with some sort of enhancement of production of the baryons as we go to more and more central collisions. So there's a explanation of this. So here's another plot that here at low transverse momentum we have these differences depending on the centrality of the collision, and there are some theories to try to explain the shape. Seems like there's some sort of quadratic rise here, and then there's some sort of turnover like this. Now, the idea, one of the proposed explanations of what's going on here is that at high momenta, at high transverse momentum, there's something called fragmentation. Sort of the idea of fragmentation is that you have this quark gluon, you're in this quark gluon plasma, and we have a quark, and it's coming in, and it hasn't decided what kind of hadron it wants to become, but it just sort of, there's some probability for it to become anything, maybe pions, maybe protons, maybe lambdas, okay? But it doesn't, it's sort of equally likely to become one or the other, okay? And however, that seems to be describing what's going on here at high momenta, that there's some sort of universal behavior describing what this quark will become, whether it will be a part of a pion, part of a proton, or part of a lambda. Now, the idea is that at lower transverse momentum, it doesn't work quite like this. There's not this sort of disconnect between what the quark is doing now and what it becomes later. Instead, the idea is that there's a hadronization problem, that there's a hadronization situation going on here, where the quarks are still somehow confined within a hadron. They're contained within some hadron. Let's say they're one of the three quarks in a proton. So it remembers that it's coming from a proton, and so now when it wants to become some other particle, let's say we want to have a collision with another proton, it actually remembers that it's part of this proton, and that will influence whether we get a proton-antiproton collision, or proton-antiproton outgoing state, or we end up getting a pion pi plus pi minus state, which may be suppressed in this case. So the difference is that at high momentum, there's sort of this randomization of what the quark will do, this fragmentation, okay? That it becomes one of these hadrons, and there's some very simple rules for the probabilities of each. Now, however, the idea is that at lower momenta, the centrality of the collision, that's why there's all this dependence, they remember what hadrons these quarks are coming from, and they depend on the wave functions of the outgoing states that they're producing. So it's a more complicated effect, and so there's factors of the overlap of the wave functions that are producing these patterns depending on the centrality of the collision. Okay, so let me then wrap up what we learned from heavy ion collisions, and I'll talk briefly about the electron-ion collider. So what have we learned from the relativistic heavy ion collider and the Large Hadron Collider in the realm of heavy ion collisions in the quark gluon plasma? So we got some picture of the geometry. Remember, we talked about the size of the quark gluon plasma, the dynamics and the evolution of this plasma. Okay, so remember we talked about things. Well, we'll mention that in a moment. And then we looked at particle ratios. For example, we made a connection to some sort of a thermal distribution, the Boltzmann distribution, and we were able to determine what is the critical temperature from the heavy ion collisions. Now, then we also talked about this evolution as being described by hydrodynamics, that we have some flow with a very low shear viscosity, but it seems like there may be a minimum, a quantum minimum to the shear viscosity over the entropy density, and it seems that the heavy ion collisions are close to that purported minimum. Now, we also then today talked about the radiation we see from thermal photons, okay? And then we also talked about these virtual photons that are coming out as dileptons, and we looked at the in-medium modification of these meson resonances like the Rho meson. And then we also then finally talked about the baryon meson anomaly, the idea that at these lower transverse momenta, below 7 or 8 GeV, that the production is not the simple sort of probability of a quark becoming one or the other hadrons, but rather it remembers what hadron it was belonging to, and there's some overlap factors between the incoming and outgoing hadron wave functions. Now, to finish today's lecture, though, let me just briefly mention something related to all of this. That's the what's called the electron-ion collider. So perhaps you've heard of this, but the electron-ion collider is the next big machine for nuclear physics that will be built. That's the next one after FRIB, which obviously we're finishing here at Michigan State. And so there was a competition between two different laboratories, between Brookhaven and JLab, to be the site for the electron-ion collider. And it was just announced in January of 2020 that the what's called the EIC, the electron-ion collider, will be awarded to Brookhaven, and the amount is something between 1.6 to 2.6 billion dollars, and it will be completed by the scheduled completion hopefully would be by 2030. And so the idea of the electron-ion collider is that we have this ring where this will all happen at Brookhaven at the relativistic heavy ion collider. So what they're going to do is put an E in front of it, call it ERIC, for the electron ion collider. So ERIC is the electron ion collider at RIC. Okay, and so we already have these heavy ions going around in circles, and usually we bang together two. So we have two counter-rotating. Let me show you another path of ions that collide with each other, but now we're going to have one of these be actually an electron. So we have then the storage ring for the electrons. Now, as we mentioned at high energies, it's rather difficult to have this low mass electron going around this ring, so there are a lot of technological challenges to having this high energy electron going around in this ring here. But that's hopefully the challenge that they will meet. And so then we'll have a collision between the electron and the ion. And so this will address problems that we have not been able to address. So there are many interesting questions that we can try to understand. So for example, one of the questions is, so we have all these nucleons in a nucleus. We would like to know how the properties of the nucleon, the structure, the quark structure of the nucleon, is modified when the nucleon is inside of a nucleus. This is one of the questions that the electron-ion collider will try to explain. Another thing they would like to try to explain is from the heavy ion collisions at RIC and at the LHC, there was something called something called gluon saturation, where you sort of have this, sometimes it's called a color glass condensate. We have some sort of at high relativistic energies, what we see in the structure of these heavy ion collisions is that we see lots and lots of gluons. As we go to higher energies, we see lots and lots of gluons. And at some point you see some saturation, and you form this condensate, the color glass condensate. And one of the objectives of the electron-ion collider is to try to probe this, whether this color glass condensate is correct or not, this picture of gluon saturation. Some other things people are looking at are the proton spin puzzle. We talked about this before. Where is the spin of the proton? Is it carried? So if we have a proton, we know it's spin 1/2. Is that carried by the quarks? The intrinsic spin of the quarks, the spin of the gluons, the orbital angular momentum of the gluons, or the orbital angular momentum of the quarks. And so there's some hints as to a lot of this is carried by the orbital angular momentum, but that's something that hopefully the electron-ion collider can explain for us by observations. So I'll stop there, and next time we will talk about medical isotopes, something completely different.